Welcome to part 2 of my Californian job mission vlog. So now I'm gonna show you the talks from the summer school that I found the most interesting, some few shots of LA, and then very quickly I'm gonna pass through my stay in Santa Barbara and Berkeley. Stay tuned!
Email later on. Okay, first of all, today is like 20th. What the day it is? Everyone know? Yeah? Look at my t-shirt. Yeah. It is the 50th anniversary of the day that the man set the footstep on the body that is not Earth for the first time in history. So I think the mankind will forever remember that day. So this is a great day. You know, a very typical decision theoretic handling of risk is like this. You know, you always minimize something to, come up with your plan, right? And you minimize your expected cost. And let's say X is a state. Some of them are failure states, right? So this I fail, this is 1 if X is a failure state, 0 if it is not a failure state. So you penalize it. Then you get some plan that drive you away from the failure states, right? If you can come up with the value of life of Neil Armstrong, yeah, of course you can just do this. But I know that the insurance companies are doing this, of course. That's why you have to go to NASA instead of insurance companies, okay? He famously said, failure is not an option. Which is great, a strong word. It's really encouraging people. However, if you formulate what he said mathematically, saying that the probability of failure has to be 0, and then, of course, often you get no solution at all, right? So you have to say failure is an option. Then what's the right way to formulate this, right? So that's why often the risk-bounded formulation of the planning under uncertainty makes practical sense. This is the a part of the Mars 2020 landing site. It is called Jezero crater. This about 4 billion years ago, this crater was a lake. And there's a river flowing into the lake, and there's a delta. So the mission of the Mars 2020 is to go to the delta, because delta is essentially a deposit from the river, which collects all the samples from the upstream, right? So if we can find ancient life on Mars, that should be in this delta. And this cliff, this is the edge of the delta. So this is where we are going in 2 years. And then this is the classification came up with given by Spock, which is pretty good. These are the application for the rover-based images. And this is the movie for the onboard deployment.
Spock Lite is an onboard terrain classifier compatible with the RAD 750 class CPU and capable of identifying sandy terrain in images. In this movie, red represents a high probability of sand. Spock Lite is based on linear SVM, one of the simplest machine learning algorithms. It is trained by a few hundred labeled images. Spock Lite was tested in 2 ways. First, it is deployed on the Athena test rover and tested in the Mars yard. Second, it is tested on the NavCam images from Curiosity. The pixel-wise accuracy measured by cross-validation is 90% in the Mars Yard and 78% on the NavCam dataset from MSL. The estimated running time on a RAD 750 per one NavCam image is 3 to 5 seconds. Spock Lite was integrated with two navigation algorithms. One is Morphin, essentially the same algorithm as MSL's and MER's AutoNav, but implemented for the Clarity software framework. The other is CL-RRT Sharp Path Planner, a variety of the widely used RRT algorithm, which is known to perform well in a cluttered environment. The integrated capabilities were tested on the Athena rover in the Mars Yard. As a result of the development and validation efforts, Spock Lite has been matured into TRL 5 to 6.
But very briefly, what we're talking about when we talk about RL is some complex agent like a robot interacting with the world by taking actions in the world and then receiving back something that looks like a state descriptor and a reward R. And what you want to do is you want to build a policy pi that maps these state descriptors to these actions so as to maximize the sum of these R's. Okay. So why as cognitive roboticists do we study reinforcement learning as opposed to all the other types of machine learning? Why is it the most important one, in my opinion? Because there's an agent at the center of it, right? It talks about the control interaction between the agent and the world. Okay, what are AI? If you open up, what is AI about? If you open up the AI textbook, the first thing it will say is that it's about agents interacting with the world. Okay, so here is an agent smack bang in the middle of this paradigm. That is why we study reinforcement learning. So imagine the problem of being at Brown. Here's my robot. It's at Brown, like I was yesterday, and it decides that it would like to go to USC. Okay, I want you to think about that journey. Try not to think about the specifics of my journey in particular, though, because that landed up, sleeping on the floor of Chicago O'Hare last night. But think about the problem generally of how you might do this. Okay, how many footsteps are involved? How many footsteps? Lots of footsteps. I have a pedometer in my phone, so it says about 5,000 last night footsteps involved in this journey. How many decisions had to be made? How many gigabytes of data did I observe along the way? Now, if you think about learning that as a flat task, it just seems ridiculous. Nobody goes back and forth between Brown and USC thousands of times or tens of thousands of times in order to get a multi-thousand step plan to work. On its face, that's nuts. You would never do that. Right? Totally crazy. Of course you would plan. Of course, in order to get from there to there, you would think, well, first I'm going to go to the airport, then I'm going to look up what terminal I'm at, then I'm going to go to that terminal, then I'm going to get on the plane, then I'm going to hang out on the plane, which is boring, but I don't have to do anything, then I'm going to land at my airport, then I'm going to have to replan because my plane's delayed. Okay, that's how you think about it. Right? You think about this at different levels of abstraction, right? Very different levels of abstraction, except that you weren't given those levels of abstraction when you were born. No one was born knowing what an airplane terminal is. No one was born knowing that they can just hop in an Uber and will magically arrive somewhere 10 minutes later. And no one was born thinking about like how many steps they have to take to get from here to LA. Saying I've got an agent with a complex sensory motor space. This is an MDP. It's not really an MVP. We're going to pretend it's an MDP for this talk. States, actions, reward, transition. And then what we're going to do is we're going to build an abstract, problem-specific one that has abstract states, abstract actions, and the reward and the transition function just describe how the world works. So those kind of drop out once you've got abstract states and actions. So that means there's two questions. How do we do state abstraction? How do we do action abstraction? If we can do those two things on the fly for a new problem, then we can build a representation for a new problem. Then we can apply a generic MDP planner or whatever it is to it. Then we can get general AI. Can I move there and turn the switch? No, I can't because the cupboard's open. Close the cupboard, then turn the switch. Right? That's the kind of thing that classical planning does. But we don't want to start with that representation. We want to start with pixels. We're going to start with pixels and we're going to learn that representation. So here is an agent doing that. It's executing these motor skills. So you'll notice there are AR tags here. The AR tags are just for the motor skills. We don't use them for the symbol event. And what it's doing is it's gathering data that says, for every option, I'm in a particular thing where I can see all these voxels, these pixels in front of me. Can I execute a skill or not? Each of the skills. And then I pick one of them and I execute it, and then what big voxel representation comes out afterwards? That's the data that it's observing. Okay, so let me just show you planning with this thing. This plan takes 4 milliseconds to find. Of course it takes 4 milliseconds to find. That's a tiny MDP. Okay, but that's the point. So that you can learn from raw sensory motor data, this tiny MDP, and then you can plan it. So I want this robot to move an object from here to there. So what does it do? Finds the plan in 4 milliseconds. First thing it does is it opens the cooler. There's the object that it wants to pick up. Does it pick up the object? No, because the door's closed, and if it picked up the object, it wouldn't be able to open the cupboard door. So first it goes to the cupboard. Does it open the cupboard door? No, because the light switch is on. If it opened the cupboard door, it wouldn't be able to put anything inside. First it turns the light switch off, then it opens the cupboard door. Then it goes to pick up the object and drops it off. That is what a classical planner classically does. So that's not the excitement. The excitement is that it's from a learned symbolic representation.
That's it from the summer school in LA. Then I moved to Santa Barbara when I stayed on holiday. I served such great time. And then I stayed in Berkeley. I visited the MPC lab. I tried to visit the reinforcement learning lab, but I couldn't, like everyone was on holiday. But guys, like in the hybrid robotics lab, they're doing something so cool with the Cassie. They're making the Cassie go on the hovershoes. I'm gonna show you the video. It's so cool.
I hope you guys liked it. If so, hit the like button, subscribe, ring that bell so to know when more videos like this are out. It helps us out so much. I'll see you there.